Hi, my name is Amit. I kind of teach data science, and I basically work in the intersection of data, visuals, and stories. And that's kind of my primary focus. So I teach data visualization, data storytelling, as well as data science.
Hi, I'm Bhargav. I'm a data scientist at Cisco, Bangalore. My specialization is in statistics and machine learning and applying it for business problems, so predominantly high tech and banking. So that's what I've done most of my career.
Okay, so this is the last session. So I thought we'd kind of start with something a little more relaxing, or maybe, so let's start with something like a language challenge, right? Because we are talking about natural language processing. So let's see if how much of the English language do we understand ourselves, right? How many of you are native English speakers? How many of you would consider yourself proficient in English? It's a fair bit. Okay, so here's the challenge. The challenge is there are these 8 adjectives, and and there is one noun, which is the knife, which is the noun on top. You need to put these 8 adjectives together in a phrase with knife, so it's a phrase of 9 words. And I'll give you a minute to try it out. You can write it if you want. You can guess. Guessing is okay.
Yes.
Yeah?
Can I guess?
Yes,
Yeah,
yes, sure.
Any order works.
Any order works. Okay. So the first hypothesis or the first answer is any order works. Is that really true? Okay, let's try it in the order it is. Old French, lovely green, rectangular, whittling, silver, little knife. Would you use that in a sentence?
No.
You would never use that in a sentence. Okay, so clearly there is more to this. Any other guesses? Okay, let me help you a bit, because I prepared for this. I do that. Here are 3 options. The first one is lovely old silver, rectangular green, little French whittling knife. The second one is old lovely French, rectangular green, little whittling silver knife. And the third one is lovely little old rectangular green French silver whittling knife. Now? Any guesses? Now it's easy. It's like 1, 2, or 3. So how many say 1? Okay, a couple of hands. Or no, more, 3 or 4. Okay, how many say 2? A fair bit. How many say 3? The majority. Okay. So by voting, which is what I was talking in the morning, ensemble modeling, by voting, we should go with number 3, right? And actually, number 3 is correct in this case, right? So there is a rule. So it's not that there is no rule in grammar on this. We go by the order of opinion, size, age, shape, color, origin, material, purpose, and noun. So the right version is lovely little old rectangular green French silver whittling knife. Okay? And it's not surprising that we don't know this, right? Because we may know how to speak before we know how to maybe construct a grammatically correct sentence. And we may be actually constructing the grammatically correct sentence, but not be aware of this, right? So this was the tweet from The Eloquent of English, I think is the book by John Wright, in which this was picked up from, and it was pretty viral maybe a few months back. So we know the grammar, maybe just by practice, but we don't really know what the grammar actually is, right? And that makes natural language processing a bit hard. Maybe much more harder than pure numbers that a lot of us are used to. I do a lot of machine learning, and for me, tabular data is much more comfortable, much more easier to handle. I can view it easily in a spreadsheet or a database, and I'm comfortable the moment it comes to number. When it comes to words, it's a little bit harder, and maybe it would be the case for some of you. So, but natural language processing problems are there in many contexts, and we come across them when we have a text and we want to summarize it. So anybody's ever used Word and tried to create a summary of the document and seen how terrible it was? But in principle, that's kind of summarizing. I have lots of text, I want to summarize it down, right? Or I want to classify a text and say whether this is spam or this is not spam. Or I want to do, which is a very common exercise as you learn machine learning or NLP, is I want to understand the sentiment of a sentence. And if you extend from sentiment, from positive, negative to maybe emotions, I want to understand more of that, right? And if you go further, I have a set of documents. I want to understand the topics around it. If I want to recommend another topic book to someone based on a book somebody has read, then it's recommendation. Or I may actually have a script or a text and I want to grade it, right? And say whether this call center call that has come in, which is converted to text, is the person likely to default or not? Or it could be a simple example as, should I give an A+ or a B- on this essay, right? They're all natural language problems. And we always come across them, right? So it's interesting to see how we can develop some skills or develop some ideas around how to approach them. So the plan for this session is broadly this. I used to teach text mining, or I teach text mining, and largely been teaching it from a very statistical learning perspective, right? And I'm sure many of you may have picked it up. Also pick up a very statistical learning approach first using NLTK or Spacey, and kind of pick up a very statistical. And one of the things I wanted to, or we wanted to accomplish in this session was kind of show a path from a statistical learning background to maybe how you could think from a deep learning perspective. And so this is likely going to be your first steps. So this is really introduction, kind of a very primer on this. We were actually scheduled to, well, we had pitched for do a workshop on this. So this is more in that spirit, take an example and run through the steps of doing this so that we can illustrate where the differences between traditional statistical learning would be and between natural language processing using deep learning would be, right? And talk a little bit about how you could start to do this on your own once you have got a sense of how this goes about, right? Does that make sense? Yeah? Okay. So the NLP learning process, and actually this is kind of a very generic data analysis process, but if you were to think about how an NLP, how it will apply to a natural language process, is we want to first frame the problem. We want to define a problem. We want to then ingest the data, the text data around it. We need to wrangle it, clean it. We need to create features from this text. Explore the data, so we may need to do some feature selection and then imply a model on it and then be able to communicate the insights that come from the model, which help us answer the solution, right? So a pretty standard process, and we'll try and walk through this to see how we can apply this on a text situation. So we're going to take a simple case. Both Bhargav and I are based in India, so we come from Bangalore. And one of the things that is pretty hot in Bangalore, no, Bangalore is normally very cold and more nice, but which is a really hot topic is demonetization, right? So, and it's kind of like a black swan event because you don't know when it'll occur. And when it occurs, the impact is very unpredictable. So we're all kind of struggling for cash in trying to be a cashless society. We're all struggling for cash. So that's where we wanted to pick up. So what is demonetization in kind of mid-November? or early November, the government announced that we're going to demonetize these two notes, which is the INR 1000 and the INR, so Indian rupee 1000 and Indian rupee 500 note. And those is what the notes are, so they are no longer legal. And it would not have been a big impact because demonetization has once happened in India in 1971 when the 10,000 note was demonetized, and barely anybody had that at that moment. But this is a visualization that I created around the share of notes, which goes from 1977 to 2015. And as they progress, you can see that, and it stops at 2015, bulk of the notes that we use in India are actually 500 and 1,000 rupee notes, right? So the share of notes is in excess of about, I think 70% or 80%. Yeah, 80%. If I got my rectangles right, yes, it's probably around that. And so it is obviously a very divisive issue and had serious impact on everyone. Well, not so much on us, but definitely much more on people who live much more on cash. So we have got a lot of reactions and tweets around that. And kind of keeping in the spirit of a grammar tweet, we wanted to kind of pick this up and say, okay, what are the tweets that are around demonetization and what, and try and look at that. And that grammar tweet had about maybe in excess of 70 plus 120,000 retweets and favorites. So we would definitely consider that as a viral tweet. So our framing for the problem is how can we create a viral tweet for demonetization? I will confess at the start, we will fail at this at the end. So the story is pretty, is not going to be, but the idea is through this process of trying to create, we will share how we could probably do it, given enough compute resources and maybe data, right? So, but at least the process would be clear, right? So we want to create a viral tweet on demonetization, and let's approach it a very traditional way. So how you would do it in statistical learning. So the very traditional way of framing this problem would be, okay, someone has to write a tweet. Someone has to write a tweet. Then we put it in a classifier. We calculate the probability of this tweet being high to be viral. If that's the case, we post it. Else, we go back to step number one, right? So a four-step process. And the idea of that problem would be, can we predict the probabilities for a tweet to go viral, right? Does that make sense? That's a very traditional statistical way of framing it, right? But we want to be more ambitious, right? As Calvin here would be trying to create, let's say, the equivalent of a BuzzFeed or an upgrade, BuzzFeed type headline. We want to learn from the historical tweets and algorithmically generate a viral tweet, right? So we don't want to do the hard part of writing the tweet itself, right? And that's something that you cannot really think about in doing in traditional statistical learning. It's harder to do. It may be possible to do, but I think it's definitely much more harder to do, right? So we need to frame it a little differently. So how could we possibly frame it? So the revised framing would be to generate a tweet algorithmically that is likely to go viral, right? So we've flipped the problem around. Now we're not testing for a probability of whether it's viral. We want to use the label of something being viral to say what the text should look like and generate it, right? So it's a very flipped example from what we would typically pick in a statistical learning approach or an ML approach, right? That first part of the framing is actually very different in deep learning. And, or it's maybe because deep learning enables it, we get into this territory of text generation, which was not one of the entries that I shared earlier on in the 6 types of problems that I talked about in NLP, because now we're really doing text generation, right? So the framing itself is different, and that takes a little bit of time to get used to, or at least did take us a little time, or me for sure, to get used to. Is that okay? Yeah? Okay, so we need to acquire the data. So the second step is acquire the data. So we need to get the raw tweets for this to generate it. And this step is probably identical. You would do that either way in either of the cases. And so you can obviously try and write your own parser, which will access the Twitter API, the REST API, or the streaming API, get the data if you want. Or you could use a Python library like Tweepy. And the main issue is really managing the rate limits around it. We use something called Tweezer, which is an open source library with a couple of people that we work with who have written, and it's freely available. You can download it, and it can access streaming data very easily. It's just a jar file. You set it up, and you can start getting in data, right? So we got about 30,000 tweets for the last 1 week, right? So that was our data set to try and address this, right? Or answer this question, right? So step probably identical to either statistical learning or this, but now we need to refine it. We need to categorize a tweet as viral or not, right? And that is kind of the labeling problem that we need to have. So we need to figure out a way to say whether the tweet is viral or not, because based on that label, we can then identify and teach or make the model learn about it. So we would choose, as Occam's razor, kind of the simplest approach possible, to label if a tweet or retweet plus favorite is greater than 100, then we label it as viral, else we label it as normal. Now, definitely we are not in the 120,000 territory. I don't think anything in our data set was even close to that. But that's a way to say, okay, what is likely to spread? And this may not be fully accurate, as our small models, there are other influences to why somebody tweet goes viral. It may not be in only the text. So you can add more features to it. So what the user was, how many followers does he have, and other elements into the design to say, okay, it's not only about generating a tweet algorithmically, it's also about finding that person who should tweet this tweet that you generate algorithmically, right? And you can kind of build on this problem. But so far we said, okay, this is the label, and then we can use it to tweet it, use it to generate the text. We would do the standardization of the text, which is pretty standard, remove the stop words, stem the data, and then remove some URLs, RTs for retweets, remove hash line, new lines, remove new lines, which would all be there, right? So this is standard cleaning stuff, right? Step 2, step 3, identical, right? Step 4 is where kind of the difference kicks in about creating features from text. In the traditional method of statistical learning, we would probably end up going and doing 4 of these approaches. So we do a TF-IDF to find what is the importance of a word in the tweets or in the corpus. So the document here is a tweet. We'd probably do a bag of words to count the occurrence of a word in a document. We'd do n-grams, and maybe do 1 n-grams, maybe 1 gram, 2 gram, bigram, up to trigram, maybe bigram, right? Bigram, because it starts to explode really well. And maybe do entity and pause tagging. So we will do entity, transform the feature into entities, do part of speech tagging, and do that. And this method is very valid and is widely used for the last 20 years, 15, 20 years. But it is inefficient. And it's inefficient largely because of 2 reasons, or 3 reasons. One is it creates a very sparse input matrix, right? So the input matrix really explodes. The more bigrams, trigrams you create, for example, the matrix will explode, right? So the inherent input matrix that goes for training the model is sparse. And the input data, as I said, can then very quickly explode because we're using a sparse representation to do this. And more importantly, when we're trying to create the sentence, it's important to understand the context of the sentence. And that's one thing that is really hard to capture in any of this statistical modeling techniques, right? So the context is lost in the encoding. And I think the example here is a quiet crowd entered the historic church is not equal to a historic crowd entered the quiet church, right? And I don't think if we do only unigrams and bigrams, even trigrams, even quadragrams, we will be not able to capture this context, right? So that makes sense? That makes sense? Yeah? Okay. So fundamentally, the deep learning approach is to do a low-dimensional but a dense vector representation of this, right? And there are two ways to do this. We can take the characters that arrive and tokenize them. So this is the tokenization which is different from what we're doing in statistical learning. We're not tokenizing by entities and pos tags. We're trying to tokenize by characters and trying to understand which character comes after each one. Or we can tokenize the words. In our case, we chose something which is a character tokenizer because literally we were running it on a computer, and it's much faster to tokenize by characters, and it's much more memory efficient, right, to do it by characters. But both are fundamentally okay. You can also do, both are okay. It really depends on what your data space is and how much memory do you have and how you can actually operate around it. If you go to characters, you can probably do something with 30,000 tweets. If you are at words, you'd probably need an order of magnitude more, or maybe even a couple of orders more before you can create any legible tweet. Okay. So far with me? Now, how do we create this vector is you need to learn high quality word vectors. So we need to create this vector, and we want to find those vectors of words that are close to each other, right? So the example here, for example, is Cavs are the NBA champions, and that's just because Bhargav is a basketball fan. Cavs are the NBA champions, and the vector hence would kind of look like this, right? So the idea is to map these words into a vector space where we're trying to measure the similarity between the words using this word vector, right? Word vector. And the approach to do this is, one of the approaches is to do word2vec, which kind of combines two approaches, right? One is to capture the context that we didn't capture in statistical learning. So how do we capture the predict the word using what is called a skipgram? So an example of a skipgram would be 3 words before, 3 words after. So that's like a skipgram. So now we have a 7 word that we're trying to keep track of. And the other approach is kind of continuous bag of words. So we're predicting the context of the word, context given a word, right? You want to elaborate?
Yeah, I mean, so this was developed by Google in 2013. One of the most popular ways on how to do word embedding to create vectorized representations. So like what Amit told, so if you have demonetization, understanding what other words would come along around that's the context that would be provided by continuous bag of words. Given a set of words around a particular word, predicting what that word would be, an example of skipgram. Right, so these two would be used to create word vectors like what we saw in the earlier slide. This is a very popular example on how word2vec is done. The interesting thing is it almost lends itself to basic mathematical vector operations like the word vector of a queen. If you subtract it with king, it's the same as a vector of woman subtracting it with man. It's also the verbs are close to each other, and this been examples where the country capital mappings have turned out to be well. So this was done on a really large corpus of data. So this is an example of something what we call pre-trained models. We'll talk about that later in the talk, but just remember that these are things that's already available. So if we use any library that already implements word2vec, it's just one line of code to get a vectorized representation of a particular word.
Okay, so typically the next step would be we would do some kind of feature selection. And the advantage in using, then feature selection is typically kind of a manual process in the traditional statistical approach. The advantage with doing it with deep learning is because we're trying to create this network or a deep network, we're trying to get the network itself to do feature selection. I mean, that is the principle. Many of you are aware of that. You know that the network is trying to identify the features through the hidden layers, right? So feature selection in our case will happen automatically. And what we don't need to do is then manually try and find these features. So we can kind of skip the step.
So an example is in traditional methods, you'd have TF-IDF, bag of words, or skip n-grams. It's kind of hard to tell beforehand what all features you need to add. So you need to keep experimenting with various setups, and because it's sparse, it's kind of hard to scale to many algorithms. But here, all you need to do is just one low-dimensional dense vectors, and you're good to go for the next stage.
So apart from the framing, the fundamental thing to remember in the representation is basically the difference between a sparse matrix and a dense representation. Because we have a dense representation, we can run a neural network on top of it. I mean, and that fundamentally drives whatever benefit we get out of it. So that part is kind of a tweak from what we would, or what I would be doing earlier in statistical learning. Right? Okay, model selection. Every time I've attended a deep learning conference and I've asked people why they chose the model they chose, they will always come back and say it's an art. You know, it's an art. And to a large extent, it's a lot of, maybe it is an art. I don't practice it enough to confess, know enough about it to say how to design neural networks. But the art has revealed that the network that works best for trying to understand context is recurrent neural networks, so RNNs. And the idea of RNN is that what I want it to learn is not just something about this word, but also to have some kind of memory in the system so that I can remember what word passed before it or what word passed after it, right? So that's kind of the idea of having some kind of memory to maintain in that, right?
So in the way traditional neural networks were designed, we were all feed-forward networks. You would have input layer and a bunch of hidden layers where computations happen, and that gives the output. Information passes always from the left-hand side to the right-hand side. There was no feedback available in traditional neural network architectures. So over time, these things evolved, and it's not that these networks are fairly new. They've been there for a while, but then newer advances in algorithmic design figured out that, okay, how can we avoid overfitting? How can we make it train? How can we persist memory? So these things happened along with large corpus of data, led to recurrent neural networks being widely used in NLP in the last couple of years. So the main advantage over here is that it will be able to persist information. So we have to decide how long it has to persist information, but that's the key differentiating factor over here. This is an example where, given the context, I grew up in Brazil and I speak, so you'll be able to relate Portuguese because it maintains that it's in Brazil and speak as a language, so you'll be able to relate to that. The key concept, so when you have feedback, so how do you represent that to do training? Something called unrolling over time is done, where you deconstruct a feedback loop into a feed-forward network. The way it's done is through sequences, so you have to think about any particular operation as a sequence. So if you want to recognize image and explain it into words, that's an example of a sequence. A sentence and classifying its sentiment is still a group of sequences into one sequence. This machine translations are, you take a text and you generate a text in another language, or a video the task classification of a video is a real-time classification task, right? So these are all sequences converted to sequences. This is an example of how unrolling happens. So on the left that you see over here, you have the node where information can persist for some time. When you unroll it, you specify how long this information can persist. A very typical architecture that's used in recurrent neural networks is called LSTM network. It stands for long short-term memory network, where you persist this information for a very short period of memory, but you do very long sequences. So you can remember sequences for a very long time, but within a sequence, the memory is there only for a very short time. So that's an example, a very popular RNN framework. The other is gated recurrent units. LSTM is more widely used.
Right. So if you talk to anybody who's doing NLP, they'll talk about, or deep learning, they'll talk about what is the architecture, right? So what is the architecture that we've used to go through this process? And is this an architecture that you can think about which would work? So we've talked about acquiring the data, getting the tweet feeds, talked about pre-processing them, and we use Spacey to do that. Getting it into character tokens, right? So we then vectorize the tweets, convert it into character tokens, and then we're trying to learn the sequence through an LSTM two-stacked network, right? And based on that, we will then get a random pattern input sequence, predict the next character, append it to the sequence, drop the first character, and predict the next character, right? So this is a generic architecture that you can follow. The two things to kind of learn or make the system learn is the character representation, which is the word-to-vec. So you can start with word-to-vec, but you then need to train it to your corpus so that it learns more specifics about your domain. And the second is to fix the architecture of the LSTM. The main challenge that that we've come across in trying to do this is mostly figuring out a way to represent data. When we try to do music generation algorithmically, how to represent the music, to remember the notes, was the main challenge to figure out. Once we figure that part out, the rest of the network is, as I said, an art, right? So you learn by copying, you learn by seeing what others are doing, you implement that, and then you tweak them, right? And that's kind of the good thing about trying to use neural networks. So what was the answer that we got using this? We really ran it for very few epochs, but if you kind of see the tweet, and we should probably have put it in a tweet box, it said, of course, benefits the internet service. So one of the criticism in India is really that the cashless move to demonetization has really benefited all the cash wallet people. So this tweet doesn't occur in the original tweet. I mean, though there are parts of this in there. And the second one, which is after a little bit more epochs, is a little more not that clear, but clear. It starts with clear, though it's not clear. Clear, aimed at rescuing the banking sector, not for anything black money. HT is now becoming clear. Okay, aimed at. Now this is a network we had very little data, 30,000, trained it for very little time, 20 epochs, and I won't go into the details of how to think about loss and how to see whether the network is learning or not. I mean, that's something. Maybe as a longer session.
So a couple of things over here, right? So when you start training, it really threw in a very short sentence. I mean, it's like literally like 30, 40 characters, but then as it keeps training for a longer time, it grew. So this was like within a minute, and this I think was like 10 minutes of run. So as you train more, it starts getting better. It still makes mistakes, but it's definitely the loss function has reduced, and it starts generating something better.
We are very practical practitioners, right? Or in my case, more trying to teach, and Bhargav's case, trying to practice. So we really want to think of when can we use this and how can we use this, right? And there are basically 4 challenges which we come across every time we try to do something using deep learning, right? One is the data size. So RNNs don't generalize well. Fully connected networks, which is kind of the closest proxy to ML, generalize very well on small data sets. RNNs don't generalize on large data set, small data sets. So you need really a large corpus for it to train. And you need to make your word embedding as specific as possible to it. So we use word-to-vec as a standard model, but you need to train it word-to-vec for a far longer duration to make it more valuable. The deeper your network is, the more learning is possible to happen, right? So the more deeper the network would basically mean the more deeper the network, the longer it takes to run it, the longer the training time, the longer the compute you need to, well, not the compute, the GPU need to run it to kind of make it happen, right? And that, to be honest, that makes a little bit harder for somebody who does not have an enterprise resource behind it, or does not have a GPU lying around in his house to kind of try this out. So if you're trying to learn on this, that's one of the challenge. If you have a machine accessible or GPUs accessible, you can actually run this fairly quickly and try and learn and iterate. But if you don't have access to that, then it makes it much more harder to do learning for yourself on how to learn, make them learn, right?
So the year of 2016 is the year of chatbots, right? So this is an example. So where do we go from here? It would be something deploying this in chatbots, creating models for chatbots. Of course, we chose a very simplistic character tokenization, but you would do word embedding, and you could do domain-specific stuff. So if you want to build something for a customer support or a help desk support, you would take domain-specific knowledge and use that to create word vectors. The standard thing is to take Wikipedia data and do that. But if you have very specific information, you could do that. And based on the questions that comes in, you can parse it, you can understand and generate responses based on that. So if you look into the architecture that we showed, it was just predicting the next character, and you could do that to predict the next word or the next sentence. And that's the underlying principle on how chatbots are designed.
How do you get started? Pretty practically, these are the tools. If you're on the Python stack, so if you're not on the Python stack, maybe there would be other recommendations. But if you're on the Python stack, using Spacey for pre-processing is pretty good because it has industrial strength, or at least their logo is industrial strength for text processing, and it is pretty decent. Using GenSim for word-to-vec training. And then fundamentally, Keras is the best one to start with because it's easy to get started with, and you can then put the backend of TensorFlow to train it, right? So these would be the three things you need to. Always start with a pre-trained model. So use a pre-trained model like word2vec, and also similarly a pre-trained RNN model to really shrink this process of learning, right? So you always start from there, and so the idea is to pick word2vec or a pre-trained model to go there. Okay. Hardware is a hard question. It has to work on GPUs. If you Titan X is good if you are on the consumer end, which means trying to do this as your own hobby or trying to beat Kaggle competitions. If you are on the professional end, maybe Tesla K80 is the better recommendation. But better than us, you can go to this blog post, which is probably the go-to guides to kind of think about hardware choices when you're looking at training deep learning networks. Okay. Closing thought, I mean, this is really a short talk, so it's not enough for us to cover how to really do that. But Bhargav has actually, and we have kind of created a notebook and workshop material which is probably more detailed. It's 1 day long, and it goes much more details around how a neural network works, how does the backpropagation algorithm works, how can you train it on word embedding, on word2vec, how can you get started on Keras, how can you use multi-layer perceptron, how can you add CNNs and RNNs together to do text. It's all on text. It was done very recently at the PyCon Europe. So it's just in June or July? July. So it's pretty decent. It's a very good starting point for somebody who wants to try and pick up how to do this. And I would recommend it as a good resource to do that. Whatever we've done on this exercise, we'll also come into that as an example. So you could follow this repo or star it and and use it to start your own journey on how to do text or how to do NLP in deep learning. That's the two of us. Bhargav is at Bhargav on Twitter. I am at Amit Caps. My website is amitcaps.com. Feel free to reach out to us if you have any questions. You can raise an issue on GitHub if you think there is, if you have a question there, raise it on Twitter. You can reach us on email. Feel free to reach out to us. We'll be hanging around here for some time. And if there are any questions at this moment, because we still have time, and it's the last talk, so we can talk, we'd be happy to take it now.
Yes. Good.
Actually, in your tweet, when you showed, there was a punctuation mark also. But in the previous slide, you had said that you have removed the punctuation.
No, so we don't remove punctuations. So so the way it's typically done is you create your regex and you tell what you want to remove. We don't remove punctuations, but you remove other. Right.
One slide you had said that you removed all these.
No, stop words are removed.
Stop words are removed.
But yeah, I mean, it requires traditionally less text processing than you would do in statistical. In statistical, you'll be very clean. I want to remove every stop word, every punctuation, and everything. Here, because you want the context, I'm not even sure whether it's beneficial to remove stop words. You may actually, yeah, you may actually even keep them. Correct.
Right.
Correct. You don't want to remove that, right? So this is a toy example.
Some pre-processing, like you remove RTs and things like that, but yeah, not numbers. Someone else had a question.
Someone else have a question? Yes.
Yes. So that's a very active area of research, right? So one thing is to do pre-trained models. So there are two challenges. That's one thing. The other thing is the size of the network is huge, and if you listen to some of the talks here, more focus on how do you do things in production. And for example, if you do fraud detection on e-commerce sites, you really can't like score 1 million parameters, which is like 20 MB, and send it back and forth. So there's tremendous value in doing that, and that's still a very active area on how it could be done. But eventually, I think, so one of the things that we generally do is build a very complex model and understand what its generalization error is, and try to find the most simplistic model that's within a few standard deviations away from that, and use that for prediction. So that's a fairly rule of thumb work.
So I think couple of areas that I've seen where, at least for image, they've done a lot of this is how to compact the matrix, where you store it, because you want to do it on smaller and smaller devices where memory. So there are at least 3-4 techniques being explored in terms of how do I compress my neural network. And I think if you do that, then it may be more amenable to easy training. So that's another approach. I think this is really very active in some way. And to be honest, we're also equally as much as learners in this than practitioners. So, anything else? Anybody else has a question? Okay. Well, thank you so much for sticking around for the last talk, and have a good rest of the day and the week. Thank you so much.
Thanks, everyone.